3.2 exponential and logistic modeling. Okay, so as y'all pointed out, there really weren't notes for this section, but there is one thing, but we're just going to write it here. The exponential population model. So there are a few word problems in this section, but they're not like anything super crazy. If a population P is changing at a constant percentage rate, R, each year, then P of T is equal to P sub 0 times 1 plus R to the T. So this is a formula that you need to be familiar with, where P sub 0 is the initial population, R is expressed as a decimal, and T is time in years. All right, so our first problem say to tell whether the function is an exponential growth function or an exponential decay function, and then find the constant percentage rate of growth or decay. So I actually don't really do like decide if it's growth or decay kind of to like till the end, but anyways, we have to like solve it first. But 2 P of T is equal to 4.3 times 1.018 raised to the T. All right, so just looking at it, I can't, quote unquote, can't tell if it is going to be growth or decay necessarily. But I want to look at what each of the pieces of this formula are. So the P sub 0 is the number that's over here not being raised to a power, so 4.3 is our initial value. And then this middle part that's being raised to the T is 1 plus R. So 1 plus R is equal to 1.018. That means that R is 0.018. Since this number is greater than 0, that tells me then that this is an exponential growth function. And it's asking me for the constant percentage rate of growth or decay depending on the situation. So we would say that it has a growth rate of, and we turn this into a percentage, so I need to move the decimal place to the right, of 1.8%. So that's how you would answer that question. Six, G of T is equal to 43 times 0.05 raised to the T. So P0 is 43. 1 plus R is 0.05. So when I subtract 1, R is negative 0.95. That is less than 0. So that means this is an exponential decay function. Now, that means it has a decay rate of 95%. not of negative 95%. The negative means that it's decay. So the decay rate of 95%. So if it's positive, it's a growth rate of whatever the number is. If it's a negative, then we say decay rate, and we don't put the negative sign on it. Just make sure you watch that.
Wait, where did we get we just multiplied the two things and got negative 95?
You subtract 1 from 0.05.
Yeah, I subtracted the 1
okay.
to get that. It doesn't look like a 1, but there we go. Okay, our next problem say to determine the exponential function that satisfies the given condition. So essentially we're just setting up the functions with the information that they give us. So 8, they give us an initial value, and I don't care if you just write that as P0 instead of copying it over as it is, but the initial value is 52, and then they say that it's increasing at a rate of 2.3% per day. So that tells me that P0 is 52. If you didn't already write it that way, you can write it that way now. I know that the rate is 2.3% and it's increasing, so that's a growth rate. So R is equal to 0.023. But in the parentheses, when I write my equation, it's 1 plus that value. So 1 plus R is 1.023.
Oh, does that say 2.3% or
2.3. Let me fix that. It's kind of hard to see. There we go. So to write the equation, I have P of T is equal to 52 times 1.023 raised to the T. Now, it's important to take note that it says per day. When we initially wrote our stuff at the top, it was given the situation, it was per year. T is just whatever units they tell you. Okay, so in this initial thing, it was in years. However, this is giving us everything in days, so T would be in days if you were actually solving this equation, which we'll be doing in a little bit. Ten. We have an initial value of 5, and it is decreasing at a rate of 0.59% per week. So this time, if I was solving my equation, then it would be in weeks for T. So P0 is 5. Now, it's decreasing at a rate of 0.59%. So what does that mean R is?
R is 0.00. 0.59.
But it's decreasing, so what does that mean? What happened up here when I got a decay rate or decreasing?
Oh, it became negative.
It's negative. So we need to put a negative sign on that. So you got to watch the wording here. The previous one was increasing, so it was positive. But if it's decreasing, it's negative. So 1 plus R, I'm going to add 1 to this number. So that's going to end up giving me 0.9941. So my equation then, P of T is equal to 5 times 0.9941 raised to the T. Okay, so this section has a lot of stuff in it that's like bacteria growth, half-life, all of the things. You've probably heard this stuff in science, probably specifically biology. But we're going to be solving this. However, there's some stuff like this where we're setting up the equation, not like as a word problem. So we're going to look at a couple of those and what that means, if it's like doubling or halving or whatever. Because they're the ones that are a little bit harder to set up. So 16, the initial population is 250, and it is doubling every 7.5 hours. Okay, so whenever we have something like this, it changes the way that our t-value is written, okay? We have a slightly different formula when we're dealing with this kind of stuff, if it's doubling or whatever. Doubling is essentially our rate, so instead of it being like 1 plus r, when it says doubling, it's going to be a 2 that's going there instead of the 1 plus r. Okay, if it's halving, then we put a 1/2 there, or we can do a 2 with a negative exponent. That's going to allow us to see that. So, my initial population, so P0 is 250. And down. It's doubling, so that means that it's 2. Every 7.5 hours. So there's two different ways that we can look at this. Okay, typically we don't want to put a decimal in a fraction. So we would typically rewrite this. So we can either do t over 7.5 because it's every 7.5 hours. So that's what this is setting us up to do. But we can also write this as 2t, let me do it this way, over 15, which would be the same thing here as t over 7.5, so that it's written as a fraction. Now, I usually stick to t's when I'm doing anything dealing with time. However, if you look in the book, a lot of their answers, they're going to convert it to an x. I don't really know why they do that, but your variable doesn't really matter. Just letting you know. So I end up with P of t is equal to the initial 250, and then times 2 for the doubling, raised to either one of these fractions. The book's going to use the one that's like a normal looking fraction. So 2t over 15.
So why is it not parentheses? Yeah.
What do you mean?
Like the one before we put the 1 plus r in parentheses. And this one we didn't.
I technically didn't have to do it with this one because I just have a decimal. I just did it so it looks nicer. So
if
it's
you
not
wanted
like
to
times a
find-
decimal.
So the 1 plus r equals 2. Yeah.
Yes, 'cause
technically
it's doubling.
200%.
Yeah, so we're getting 100% every time. So,
Are we almost done, or can I use the restroom real quick?
I'm not almost done, but you can go. All right, 18. Initial mass is 17 grams, and it's halving once every 32 hours. So P sub 0 is 17. Now, it's halving. So I can either write this as 1/2 and then raise it to the power, or I can write it essentially as 2 to the negative 1, aka multiply whatever my exponent is by a negative, and write it that way. If you like it written that way, better. It doesn't matter. I'll write it both ways so that you can see what it looks like. Now, it's once every 32 hours, so that means t over 32. So I have P of t is equal to 17 times, I will use parentheses on this one because it's 1/2 being raised to a power. Raised to the t over 32. Or, if I don't want to have a fraction raised to a power, I can write it as p of t is equal to 17 times, I'm just going to do it in the parentheses again, 2 raised to the negative t over 32. The only time we really absolutely have to have it in parentheses is if it's a fraction like this, or if I'm leaving it as, where is it, like 1 plus r, because that is telling me it's on the whole thing, but I go back and forth on if I write the parentheses or not. This one doesn't really need it, but it's fine. All right, questions on those before we get into like the legit word problems, where we're setting them up and solving and stuff. They sort of are, just not completely. All right, an example, because they don't actually have a ton of these like word problems necessarily in here, so I'm just have some examples for you. So suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000. So essentially, I'm going to use known information to help me solve, or to like set up an equation. Now, what I'm going to tell you is to actually solve this, you technically need what we're going to be doing in 3.3, so you're going to get a little of an intro to 3.3. You have a leg up from my previous classes by doing this because we hit logarithms last year briefly at the end of the year, so you've kind of seen this before. But the initial setup is really what we're concerned about in this section. You will understand more about how to solve it after we do the next section. So, I know that I have 100 bacteria to start with, so that means that my P sub 0 is 100. I know that it doubles every hour, so that's going to mean 2 to the something. And I want to predict when the number of bacteria will be 350,000. That value is P of t. So I'm predicting when, that means I'm solving for t. So to kind of start thinking about this, I'm going to kind of just go through and do this like manually. And then I'm going to figure out how to write an equation that will set this up for me with the given information, because I think it's easier to see it that way. So at 0 hours, aka my starting amount is 100 bacteria. It doubles every hour, so that means that after hour 1, there are 200 bacteria. At hour 2, there's 400 bacteria. Hour 3, there's 800 bacteria. Okay, and so on and so forth. So, this is obviously my initial value here. So, this would tell me then that essentially this is 100 times 2 to the first. Then this is 100 times 2 squared. And then this is 100 times 2 cubed, so on and so forth going down. So that tells me that I just need to replace this number here with t, and we're dealing with number of hours. So that means t is in hours. So then my equation, I'm going to use this to set this up. P of t is equal to 100 times 2 raised to the t.
Wouldn't it be 350,000 equals 100?
Well, I am getting ready to do that. This is just my
Oh,
initial
okay,
equation. Yeah. So the equation to solve it is this, but so that I can actually solve for t, yes, that's exactly right. I'm going to plug this in for p of t. Now, because of how we have to solve exponential equations, I'm going to put the 350,000 on the right-hand side because of my little shortcut to solve them. So I'm going to have 100 times 2 to the t is equal to 350,000. So to solve this, I'm going to first divide by 100. So I'm just going to take 2 of these zeros off. So 2 to the t is equal to 3,500. Now, this is where, if you knew nothing else, you'd pretty much have to stop here. I'm giving you a little preview for the next section / a review of what we did last year. To solve an exponential, we have to use a log. That means you're going to have to use your calculator to do this. To do that, we start up here, we come down, and we go back. So this is log base 2 of 3,500 is equal to t. So to refresh on how to solve this, or how to plug this in your calculator, it's running away. You're going to hit math, and then you're going to arrow up to log base. It's option A, at least for me. If you have the newer calculators, may or may not be that. This allows you to plug in the stuff in the boxes. You obviously have a log button on your calculator, which is for log base 10. You also have ln, which is for log base e. This allows you to plug in any base. So we have log base 2, and then arrow over 3,500. And then that's going to give you a number. That's what that log is equal to. So 11.77. So t is equal to 11.77.
How did you get the log base 2
Scroll back
again?
up to the,
So hit math on the left-hand side of your calculator and then arrow up and you'll see the words log base.
Okay.
And then it'll bring it up so you can type it in. Does everybody's calculator allow them to do that? Because if not, there's a shortcut way we have to do it. Well, it's not really a shortcut. It's actually kind of longer, but.
Mazers.
All right, so at this point, this is in hours. But a lot of times, they don't just want hours. They want you to say, like, because do you really know what 0.77 of an hour is? It's easier if you comprehend it in minutes, right?
40 minutes, something like
It's a little bit more than that. So what we would do to finalize our answer is I would say 0.77 times, there's 60 minutes in an hour, so times 60 is 46.2, so we're just going to call it 46. So essentially, that's in minutes. So my final answer technically will be 11 hours and 46 minutes. And obviously, I have rounded this number at 11.77 because they keep on going and going and going. So that means that after 11 hours and 46 minutes, 100 bacteria have become 350,000 bacteria. Hence why when you're sick, wipe things down often because bacteria grows like crazy. Now, obviously, every bacteria is different. That's just this particular one. But just for you to see that. Let's see. Let's look at a half-life problem. All right. This is another example because there's not a ton in the book. Suppose the half-life of a certain radioactive substance is 20 days. And there are 5 grams present initially. Find the time when there will be 1 gram of the substance remaining. Have y'all talked about half-life in science? Okay, that might have been supposed to be last year. You might hit it a little bit in chemistry.
We also didn't really learn anything last.
No, that's what I meant. Half-life, a lot of times that's how they use things with like carbon dating to see how old things are. It's not always accurate, as we can see when people try to tell you that the earth is millions of years old. So take it for what you will, but just,
What is the half-life?
it's like how long it takes for it to like decay and break down.
So how long it takes to half itself?
Yeah. So every 20 days, this amount gets cut in half.
Okay.
And we're cutting in half until we get to 1. Basically, the 5. So, notice that T is in days this time. So I'm going to note that here. The initial amount, so P0 is 5. We're looking at half-life of 20 days. So this is going to be, instead of writing it as 1/2, typically you're going to write it as 2 to a negative exponent. So I'm going to keep to that just so that your answers will be consistent with the book. So this is a negative T over the amount of days, so 20. So every 20 days, this gets cut in half. And I ultimately want to know when P of T will be equal to 1. So to set up my equation, just the initial setup, P of T is equal to 5 times 2 to the negative T over 20. So then, just like I did with the last one to solve, the only difference is this has a negative exponent, but it's not really changing anything, is I'm going to replace P of T with 1. I'm going to do it the same way where I did 5 times 2 to the negative T over 20 is equal to 1, just for the purpose of solving it. So divide by 5, I've got 2 to the negative T over 20 is equal to 1/5. Then I'm going to use a log to solve, so I'm going to have log base 2 of 1/5 is equal to negative T over 20. So ultimately then what's going to happen, and your calculator can do this all in one thing for you, is I'm going to multiply both sides by negative 20, because that's going to get rid of it over here, and I'm just going to be left with T. So I'm going to have negative 20 times log base 2 of 1/5 is equal to T. And then you're going to be able to type that into your calculator. So before you hit log base, you'll hit the negative sign, not the minus sign, the negative sign, and 20. And then you can hit the log base, and then you can type this in. So when I do that, I get 46.44 days. Now, obviously, 0.44 days, we could convert that into hours, and then we'd have to do minutes and all the stuff. I'm just going to leave this one in days. It's typically just if it's like hours and something, a lot of times they convert it to hours and minutes, but it kind of just depends on the problem. So I'm not too overly picky about it unless it specifies how you have to write your answer. Questions on that one? I'm going to do one more half-life problem because they're pretty common ones. Okay. Then 34. So radioactive decay. The half-life, I'm not going to write the whole problem, I'm just going to do this. Of a certain radioactive substance is 65 days. So I'm just writing half-life of 65 days. There are 3.5 grams present initially, so I'm just going to go ahead and write P0 as 3.5 grams just for the sake of time because we're running out of time here. So then part A, because technically this previous question would typically be a two-part question. It would tell you initially to express the amount of the substance remaining after like T days or whatever, and then it would tell you to actually solve for the amount. But so part A, express the amount of substance remaining as a function of time. So that's just my initial equation set up, is all that that means. So I know P0 is 3.5. The half-life is 65 days. So that means I'm going to have negative T over 65 for that part. And then that way it'll be 2 to that there. Or you can write it as 1/2 to the positive T over 65, up to you. So my initial equation is P of T is equal to 3.5 times 2 to the negative T over 65. And that's all that they're looking for in part A. Part B, when will there be less than 1 gram remaining? So we're still going to set this up as if it's just 1 gram, and we'll just know that it's any point after what our answer is, right? Because really, we are technically looking for like a less than or equal to amount, but for the sake of setting it up, we can't really set it up that way. So we just have to know that it's any time after that amount of time has passed. So I'm going to replace P of T with 1, just like I did in the previous problem. So 3.5 times 2 to the negative T over 65 is equal to 1. Divide by 3.5. So I've got 2 to the negative T over 65 is equal to 1 over 3.5. Obviously, under normal circumstances, I don't really want a decimal and a fraction. However, I'm going to be plugging it into my calculator to the log, so it really doesn't matter. It's going to figure it out for me. It just doesn't look nice on paper. So we use a log to solve the exponential. So I've got log base 2 of 1 over 3.5 is equal to negative T over 65. And just like we did in the last one, I can multiply by negative 65, so I'm just left with T. So I'm going to have negative 65 times log base 2 of 1 over 3.5 is equal to T. And then you just need to type that in and get an answer. I'll let somebody type that in and tell me what you get. And just as a general rule, go to 2 decimal places with this, unless they're like both zeros, then obviously you don't need to do that.
117.48.
Okay, yep. So 117.48 days, so that we would know then that any time after that is when there would be less than 1 gram remaining. Essentially at this point there is 1, but even minutes after that there would be less than 1. So questions on this? I know it's a lot, and this is like pretty much all new information here. All right, problems, and like I said, you'll have class tomorrow to do this, and then the notes for 3.3, so you won't have any homework this weekend. But they're 1, 5, 7, 9, 13, 15, 17, 31, and 33. And there are a few other like growth and decay problems in here. They're just kind of like spread out and random, so if you want to do any more, you obviously can, but I'm only requiring you to do 2 of them.